Section 4.3 deals with precipitation reactions. It says here that in a precipitation reaction, two soluble ionic compounds react to give an insoluble product, and we call this a precipitate. Right? If you're not part of the solution, you're part of the precipitate. So anyhow, when it says here that we have two soluble ionic compounds, we've talked a lot about ionic compound formulas, and when the ionic compound is soluble, we're going to follow that up by including the states of matter, and we're going to put AQ next to that, which indicates aqueous, and that means that it's in solution. And if it's insoluble, we follow up the formula with an S in brackets, and that means that it's a solid or that it's insoluble and forms a precipitate. So it says here the precipitate forms through the net removal of ions from the solution, and we can even get more than one precipitate if we have, three or more aqueous solutions that were reacting together. So this is a picture I just took straight from the book, and the take-home message of this picture here is that you have two clear, colorless, homogeneous solutions, and we're mixing them together, and all of a sudden we form this, this bright yellow precipitate. So that tells us that there's some kind of precipitation reaction going on here. And in case you're wondering, this is a reaction between sodium iodide and lead 2 nitrate. Anyhow, we'll talk about that in a little bit. In a bit from now. Anyhow, so here's another example. This is the precipitation reaction of calcium fluoride. So in this big circle here, they're trying to show you what's happening at the molecular level. So it says we're taking a solution of calcium chloride. So calcium chloride. The reason I know it's a solution is because it's followed up by this AQ here. That means it's in solution. And I'm mixing that with a solution of sodium fluoride. So I have sodium fluoride, and I know that's a solution because it's followed up by AQ. And what happens in this reaction is that the electrostatic attraction between the ions that are in the solution outweighs the tendency of the ions to remain solvated and then move throughout the solution. So which ions am I talking about? I'm talking about the calcium and the fluoride ions. So their electrostatic interaction is greater than the interaction would be to solvate the ions in the water. So we end up forming a solid. And of course, if you're wondering, how am I going to know that? Well, you're going to have to look at the solubility table, which we're going to talk about in a second. Then if I want to write a total ionic equation, so sometimes I call these MEs, the molecular equation. If I want to write a total ionic equation, I just write out all the elements in their ions. So calcium is in group 2, so it has a 2+ charge. I have 2 chlorides. They both have a -1 charge, so on and so forth. So I break everything apart into its ions, but I will not break up calcium fluoride because it is a solid. So if it's a solid, I do not break it up into its ions. Then to make a net ionic equation, all I'm going to do is look at which ions remain unchanged on both sides of the equation. And you can see that I have 2 chlorides here, 2 chlorides here. I also have 2 sodium ions and 2 sodium ions here. So we call those spectator ions, and those are the spectator ions. So my net ionic equation just shows the ions that are involved in forming the calcium fluoride, which is our precipitate. So it says here, how do you predict whether precipitate's going to form or not? Well, the first thing to do is you have to be able to identify the ions that are present in the reactant. So that means you have to be able to look at the element and determine what the charge would be. Then you consider all the possible cation-anion combinations. So you imagine any cation that's in solution combining with any anion. So you look at all the possible combinations, and most of the time we only have a couple of combination possibilities, but we look at all of them, and then we use what are called the solubility rules to decide whether any of the ion combinations is insoluble. And any insoluble combination identifies a precipitate, so a solid, that will form. So these are the solubility rules for ionic compounds. The first 3, the reason I have the first 3 highlighted in red is because I expect you to have the first 3 memorized. So we'll put a little bracket here, and we'll say you should memorize these ones. So we'll put here, memorize. You should know these ones. So the first one is that all common compounds of group 1A ions, so that's lithium, sodium, potassium, etc., those are going to be soluble. Anything that's a compound with ammonium, with the ammonium ion, that will be soluble. And then nitrates, so nitrates, acetates, or perchlorates, those are going to be soluble as well. And you can see that the reason that I'm asking you to memorize those is because there are no exceptions for those three rules. So those ones are kind of probably the easiest rules to have down pat. Anyhow, I'm not going to go over all the rest of the rules right now, but suffice to say that I will give you this table for the next exam that covers Chapter 4. So you should just be aware of how to use this table. So let's say we were talking about a compound like lead 2 iodide. So I'm just going to write it here, lead 2 iodide. And you wanted to evaluate whether that's soluble or insoluble. Well, I'd start over here and I'd say on this part here, it says all common chlorides, bromides, and iodides are going to be soluble. But then I go over here and I look at insoluble exceptions. And let's see here. Chlorides, bromides, iodides of silver, lead 2, and this lead, oops, let me go forward here. Oops, there we go. So this lead in my lead iodide is lead 2 plus. So this is lead 2 plus iodide, so I'm going to put a solid. So that would be an insoluble compound. So that's an example of how to use the table. Anyhow, more information about that reaction. So it says here the precipitation of lead 2 iodide, we call this a metathesis reaction. And it says right here that precipitation reactions, sometimes we call them double displacement reactions. Some textbooks call them double replacement reactions, and sometimes we call them metathesis reactions. So you should be aware of what a metathesis reaction, precipitation reaction, and a double displacement reaction is. And luckily, they're all the same thing. So let's see what's going on in this reaction. I'm taking a solution, so an aqueous solution of sodium iodide, and I'm combining it with an aqueous solution of lead 2 nitrate. And if you remember, nitrates are soluble. So I take a look at all the possible ions. So if I evaluate my sodium iodide, I have a sodium ion. So I have 2 sodium iodides. So I'm going to write out that I have 2 sodium ions. I have 2 sodium iodides. So I'm going to have 2 iodides. And I just keep doing the same thing. The lead 2 nitrate is also soluble. So I write out all of my ions like that. I write out every single one. And then I evaluate all the possible combinations. Well, we've already evaluated the combination of sodium with iodide, and we know that it's soluble. But what about sodium with nitrate? Well, if you look at the solubility table, you'll see that sodium nitrate is a soluble compound. So we put AQ. And then we evaluate the last combination, which would be iodide with lead 2, and we get the lead 2 iodide, and I showed you why that is insoluble according to the solubility table. So there you go. So you know that when you mix these two homogeneous solutions, sodium iodide and lead 2 nitrate, you're going to get this solid formed lead 2 iodide. So again, the ions exchange partners in a precipitate form. So there is an exchange of bonds between the reacting species. So again, in the precipitation reaction, an insoluble ionic compound forms when solutions of 2 soluble ones are mixed. The electrostatic attraction between certain pairs of solvated ions is strong enough to overcome the attraction of each ion for the water molecules. So there we go. So let's take a look at a problem. It says here in problem 4.8, there's a couple of parts here. There's part A and part B. So it says, predict whether or not a reaction occurs when each of the following pairs of solutions are mixed. If a reaction does occur, we're going to write a balanced molecular equation. So we're going to write the molecular equation. We're going to put a total ionic equation, and then we're going to put a net ionic equation. I like to abbreviate those. And then we're going to identify the spectator ions. Who isn't participating in the reaction? So let's take a look at the first one. So I have potassium fluoride reacting with strontium nitrate. So let's take a look here. I've written part of the solution down already. So it says here the reactants. The reactants are potassium fluoride and strontium nitrate. The possible products are the combination of these ions, right? So I could end up combining potassium with the nitrate, or I could combine strontium with the fluoride. Sorry, there's not a lot of room there. Anyhow, but when I evaluate that, in the solubility table, I see that potassium nitrate is soluble. In fact, it's a very soluble compound, but strontium fluoride is not a soluble compound, so it's going to form a solid. So here's my molecular equation. Okay, I'm starting with my molecular equation. So I have my potassium fluoride plus my strontium nitrate is going to give me my potassium nitrate, and of course, that's soluble. I know that from the solubility table. And then I'm going to add my strontium fluoride, and I know that's insoluble from the solubility table. So I'm just going to balance out my equation. The next thing I do is I write out all the ions. And if anything has AQ after it, I'm going to break it apart into its ions. So you can see here, the potassium fluoride is broken apart into its ions. The strontium nitrate is broken apart into its ions. And then the potassium nitrate in my products is broken apart into its ions. But the strontium fluoride, which is insoluble, is not broken apart into its ions. So then I'm going to cancel out everything that's a spectator ion. And you see that I have 2 potassium ions on both sides of the equation, and that I have 2 nitrates on both sides of the equation. So what am I left over with in my net ionic equation? I'm left over with the strontium ion plus the fluoride ion, and then I produce my strontium fluoride, and that is shown in this equation here. So there's my net ionic equation. Let's take a look at the next example. I'll go over this one a little faster. But it says here, what if I were to combine a solution of ammonium perchlorate and sodium bromide? So again, I'm going to combine my ammonium. So I'm going to combine that with bromide. So I'll make ammonium bromide. And then I'm going to combine my sodium with perchlorate to make sodium perchlorate. So let me just write that out quickly. So I'll put my ammonium bromide, and then I'm going to end up with sodium perchlorate. Anyhow, if you go to the solubility table and you look up the solubility of ammonium bromide, you'll see that it's an aqueous solution, and that of the sodium perchlorate is also an aqueous solution, meaning that both of these are soluble. So soluble. So if you're wondering what's the answer, what's happening? Well, when I wrote out my total ionic equation, I wrote out everything. All 4 compounds are going to be written out in their as their ions, because all of them are soluble. And it says here that all ions are spectator ions, so there's no reaction. There's no net ionic equation because there's no reaction overall. The compounds all remain in solution as solvated ions. So that's kind of a funny one, but it can happen. That's a totally legitimate question to ask. Will there be no reaction? And the answer is yes. In this case, there is no reaction. So let's take a look at one more problem before I wrap this video up. So it says here, magnesium is the second most abundant metal in seawater after sodium. Okay, great. The first step in the industrial extraction of magnesium involves a reaction of magnesium plus with calcium hydroxide to make magnesium hydroxide. What's the mass of magnesium hydroxide? That's formed when 0.180 liters, so that's 180 milliliters of 0.0155 molar magnesium chloride reacts with excess calcium hydroxide. So that means this isn't a limiting reactant problem. I have excess calcium hydroxide, so I have this much magnesium chloride, and I'm going to find out the number of moles by multiplying the molarity times the volume, and I have all the calcium hydroxide that I could possibly need to do this reaction. So let's take a look at how we would do that. So the first thing we're going to do is we're going to write out a balanced equation. So I'm going to write this down. So I have my magnesium chloride aqueous plus my calcium hydroxide, and then I'm going to swap my ions. So I have 2 aqueous solutions, and when I exchange the magnesium with hydroxide, I get MgOH2 because magnesium is in group 2A. And then I'm also going to get calcium chloride. So if you go to the solubility table, you'll see that calcium chloride is soluble, whereas magnesium hydroxide is insoluble. So this is the precipitation reaction. Now we need to find out how much magnesium chloride we're starting with. So how much magnesium chloride do we start with? So how many moles do we have? Well, we know from the question that we have 0.180 liters of magnesium chloride, and the concentration is 0.0155 molar. And I'm going to write that out as molar as its units, which are moles per liter. So my liters are going to cancel out, and I'm going to end up with 0.00279 moles of magnesium chloride. So there we go. So that's how many moles of magnesium chloride that I'm starting with. And you remember that the calcium hydroxide, it says that I have excess. So that means it's not a limiting reactant problem. And probably most of you have figured this out already, that the ratio of magnesium chloride to magnesium hydroxide is a 1-to-1 ratio. But me being the instructor, I'm going to write this all out in dimensional analysis. So if I have 0.00279 moles of my magnesium chloride, and again, the ratio is 1-to-1 for magnesium chloride. So I have 1 mole of magnesium chloride, 1-to-1 ratio of magnesium chloride to magnesium hydroxide, so 1 mole of magnesium hydroxide, and I want to find the amount, so I want to find the mass, and I know that in 1 mole of MgOH2, I went to the periodic table and calculated the formula mass of MgOH already, or MgOH2, excuse me, and it's 58.33 grams of MgOH2 in a mole. So there we go. So I multiply all that spinach out in my calculator, and I end up with a mass, which is 0.163 grams.